Meeting is being live. Okay. Should I start?
Yes, Pooja.
Okay. Hello, everyone. Welcome to today's session. I'm super excited to have you all here. And I'd like to introduce Alia Verma, and who is working with us as information security consultant. And let's welcome Alia. And she's going to talk about maths and cybersecurity. I'm really looking forward for this webinar. Alia, thank you for joining us. Please start your session.
Yeah. Hello, everyone. I am Alia. I'll just share my screen first.
Sure.
I hope it's visible.
Yes.
Okay. So we all have gathered for a quick session on cryptography, the art of secret messages. So I think cryptography, the term everyone has heard of, but we will be discussing about the maths behind it. There are a lot of algorithms, there are a lot of online tools to, just get the exact value, get the ciphertext and the plain text, or like to convert the plain text to ciphertext or ciphertext to plain text. So it's important to know the maths behind it. So we will be taking some of the algorithms, some of these schemes, and then we'll be talking about it with one example. So I'll just start. So here's a quick who am I? Hi everyone, my name is Alia Verma. I am a cybersecurity enthusiast. I work as an information security consultant at KIIS. I am also a CTF player. So this is my LinkedIn handle. If you want to reach out to me, you can. Okay. So I have some of the prerequisites. I would not say that this is just like a must have. So I expect you all to know the decimal system, the binary system, the hexadecimal system, and the ASCII values. I believe little bit of programming knowledge is required, very little. Not, I wouldn't say like you need to be an advanced coder or something like that, but you need to have some basic idea of like how the ASCII values work. And then we have the modulus operation. So modulus operation is nothing but just the modulus operator, which helps us which helps us fetching the remainder. So we will definitely see more of this, a lot of this in fact. And I think in almost all of the different techniques, different algorithms, you will find this modulus operator. So moving forward. So this is still again a prerequisite. So we have Alice and we have Bob, and then we have Eve. I hope it's visible. Are the names visible clearly to everyone?
Yes, yes.
Okay, that's great. So these are fictional names. These are not like real people. These are fictional names. Alice and Bob are trying to have a communication, like they are trying to have a private chat, but the channel is insecure. So and Eve over here is considered to be the malicious actor who is trying to spy, who is trying to maybe perform a man in the middle attack, or who's trying to steal the messages in some way or the other. And the purpose is always to have a secure conversation even on an insecure channel, to make sure that your the messages that you have sent, or the personal data that you're sharing, should follow the CIA triad. I believe everyone over here knows the CIA triad, which is confidentiality, integrity, and availability. So even on insecure channel, these three should not be violated. We'll be seeing more of this, and the laws behind it, and like why this happens and all of that, and how to achieve like a secure connection even on insecure channel. We'll see more of that in the later part. I'll just quickly talk about the HTTP and the HTTPS. The S stands for secure. So that is also one aspect of it. You should have idea about it. So I'll move next. So first, we need to talk about the crypto system. What is a crypto system? The moment we start talking about cryptography, we have to first talk about crypto system. A crypto system is a five tuple, which has P, C, K, E, D. So to be very specific in mathematics, I studied all these crypto systems more with the Greek letters like rho and kappa and epsilon and all of that, and D for delta, like that. So, but for simplicity, I have taken the characters, the basic P, C, K, K, E, D. So P stands for the set of plain text strings, and C stands for the set of ciphertext strings. K is the key space. It could be in any value. It could be a specific number. It could be, specific characters as well. So all the possible keys. And E is the encryption function. So, and D is the decryption function. So there will be an E, which is the encryption function for every algorithm, and there will be a D for decryption, which will stand as a decryption function, which will be there to decrypt the value back to the plain text. So I hope so far everything is clear. Can I get a yes or no?
Yes.
Yeah, okay. Okay. I hope it's clear to others as well. Can I get more yes or no?
Yes. Yes.
Okay. Thank you. Thank you. Yeah. So we'll move to the next part. So now we need to talk about cryptology. So cryptology is a combination of cryptography and cryptanalysis. So we'll quickly try to look at, we are definitely here for a session on cryptography, but it's important to know what cryptology in itself a subject is. So cryptography is the technique of converting information to a form that will be unintelligible to an undefined recipient, and it is performed by cryptographers. But when we talk about cryptanalysis, it is the technique of breaking cryptographic systems performed by cryptanalysts. So we are not here to talk about cryptanalysis, like how to break those cryptographic algorithms. We are here to talk about the cryptography. So we'll be focusing on that. And together they form the cryptology. Cryptology can be considered a wide subject. And that's why it's not possible to cover everything in just one session. So I will definitely try to touch upon the most important ones, the ones that come very frequently to our use, the ones you will see a lot in CTF challenges as well. I'll try to cover those, okay? So I believe, again, cryptology, the concept of cryptology, cryptography, and cryptanalysis is clear. I'll move to the next one. So there's again a very common misconception between encoding and encryption. People have started using this as synonymously. People think that encoding is same as encryption. No, it's not. It's definitely not. In fact, encoding does not even count as cryptography. Encryption does, encryption and decryption does, but encoding is not. So I'll just quickly define these two concepts so that we all are on the same page. Encoding is the process of transforming data into such a format that it can be read by different types of systems using publicly available algorithms. So what does this mean? This basically means that when we are talking about any encoding scheme, any encoding algorithm, that same algorithm just converts one plain text to ciphertext. So what it does is that it will just change the format of it. And it will definitely be in a format which cannot be readable just by looking at it. You need to either use the algorithm, you need to either perform some breaking techniques to like break that algorithm, then only you can read it. And then I'll quickly talk about the encryption part. Encryption is the process to transform data so that only the authorized user who know the key or password are able to retrieve the original data. So this talks about like you need to have a plain text. You use that plain text with the help of a specific encryption algorithm, and you convert it to a specific ciphertext. But for that, you need a key. You cannot do it just like that. And that's what the second part talks about. Encoding requires only algorithm. You can use a single algorithm to encode a plain text, and you can use the same algorithm with little bit of here and there you need to make a little changes, but that same algorithm will help you decode that encoded text. But whenever we are talking about encryption, it requires an algorithm plus a key. A key is a must. It can have more than one keys as well, but a key will always be required. And the whole idea is that the person who has the key should only be able to read the data. And then again, encoding is less secure because it's just that it's just that the attacker needs to have the algorithm. That's it. But whenever we are talking about encryption, whatever the algorithm is, even if the person knows about the algorithm, they need to have the key. For example, Eve needs to have a key, which Alice and Bob share. But if Eve does not have one, she cannot just read the encrypted text or the ciphertext. Moving forward. So first, we will definitely talk about the encoding scheme. So base 64 is the most common form. There are different types of encoding scheme, but I will prefer just talking about this one because this is the most popular one. So base 64 is a binary to ASCII encoding scheme. It is designed as a way to transfer binary data reliably across channels that have limited support for different content types. Base 64, as the name suggests, has exact 64 characters. Every 3 bytes are converted into 4 characters. Okay, so last line, I hope it can be a little tricky, because if for example, you take just 3-letter word, that will be converted to a 4-letter encoded word, because it increases the length of the text increases by 33%. So it somehow adds more characters, and we'll just talk about that. So firstly, on the right, you can see that there is a base 64 index table. Okay, so we will quickly take an example. And like, I really want you all to just look at these steps that are involved, because it's very important. It requires different steps, different techniques, and it uses different kinds of, encoding schemes to finally help you encode or decode the text, the plain text or the ciphertext, or the encoded text, sorry. So the example is fun. You can see I have taken a 3-letter word just for the sake of, understanding. A 3-letter word, FUN. First, what we did, we took out its ASCII value. So F has the ASCII value of 70, U has the ASCII value of 85, N has the ASCII value of 78. So the next part is to convert it into binary. So these are their respective binary values for the ASCII, which is right above them. And then we need to convert it into a 6-bit segment. So I really want you all to look over here on the binary part. It has 8 digits, right? But what it does is that it takes only first 6. So here, if you will see, it takes the first 6 digits. It does not take the last 10. And what happens for the next one, it will take that 10 and take the remaining 4 from the next one. So here again, you can see that it has 0101 as its last bits. And then again, the 4 remaining will come over here. And then the 4 from the next one will be added to this. 2 from the next one will be added to this one. And the remaining comes in the last bit, the last segment. So this way, first what we need to do is that we need to convert the 8-bit into 6-bit. We need to club them together. So now from 3 characters, we have about 4. So that's how there's an increase by 33% if you're talking about the length. And then what we do, we just convert these values into ASCII values. This is 17, this becomes 17, first one becomes 17, and then it becomes 37, then it becomes 21, and then it becomes 14. And then we just convert it back to the actual value, which is RIVO. So I believe this concept was clear to everyone. Please let me know. If you have any questions, if you want me to repeat again, please let me know. Can I get at least some feedback, like, was it okay? Was it difficult to understand anything?
That's good.
Okay, thank you. So just take a look over here. The plain text was fun, and the base 64 encoded text became RIVO. So that is how the base 64 encoding scheme works. And there's one more thing that I want you all to remember. So there might be cases, in this case, we had exactly 8-bit characters and 3 letters, exactly 3 letters. So 8 3s are becomes 24. And 24 was able to, get segregated equally into 6-digit bits. But what if we have more letters? Like, what if we have a value, for example, 32. If we try to divide 32 into 6-bit characters, 2 will be remaining. So there's another scheme to it. That is, if 2 bits are remaining, you add 2 equal to signs. And if it happens that 4 are remaining, you add a single equal to sign at the end. So there will be a lot of cases where you will be seeing that the base 64 encoded text will have 2 equal to signs or a single equal to sign. So that is how it works. I have taken a very straightforward example where I can explain, like, how the segregation has worked. But that's an important tip to always remember that. And I think we all, whenever we try to solve base 64, it is something very common in CTFs. CTFs, you will see that a number of times there will be a ciphertext, a secret message in base 64. And I think you should I don't expect you all to manually, do this, because there are a ton of tools out there. There are online tools. There are even offline tools, there are command line tools as well. You can do it by your own. But I think it's important to know the steps which are involved into it, because at least it will help you, look at any encoded scheme and be able to recognize that whether it's an encoding scheme, whether it's an encryption, or exactly what kind of encoding scheme it is, or what kind of encryption scheme it is. So that is important to know. It always comes handy if you're solving CTF challenges. So that was it, and we'll move on to the next one. So some important encoding schemes, like some other important encoding schemes, you all must be aware that there is also something called base 32, there's base 45, base 58, base 62, base 85, there's ASCII, and there's also Morse code. So all of these are very frequently used, are somewhere very important. But again, using this as your encryption technique, or using this to, use for communication purposes, makes it very insecure, because everyone is aware of the algorithm, and even if they are not, they can use tons of tools to just decrypt it online or offline. So that again, it is not considered very secure, but it is somewhere very important, still exists at a lot of places. And I think you all must have heard of Morse code. So here is a quick example. This is how a Morse code looks like. I hope you will be able to hear this one. Just let me know if you were or not.
No.
No, it's not audible.
Okay, no issues. So this is how a Morse code looks like. You have dot and dashes. And what happens is that these dot and dashes form, with a specific combination, form different characters. It could be, specifically represent. For example, here I have taken my name, just ALYA. So a dot and a single slash represents A. A dot, single slash, and double dots represent L. And a single dash, dot, and two dashes represent a Y, and a single dot and dash again represent A. So this is how, a Morse code looks like. Encoding can also be used not only to just, have securely deliver your message. Encoding can sometimes also be used, just to make it sure that that common people, or the ones who are using the internet just like that, cannot read it. Morse code has been used a lot in the army, in the earlier days as well, but I don't think it's used that much today, because again, it's not secure anymore. Everyone knows about it, whether you're in the army or not. So we'll move to the next part. So we spoke about encoding. Now we need to talk about cryptography. There's two types of cryptography. So one is symmetric key cryptography, and the other one is asymmetric key cryptography. We all know that cryptography requires you to have a key. Fine. So we'll start with the symmetric key cryptography. So what symmetric key cryptography does is that it uses a single key to encrypt and decrypt. And it is also referred as secret key or private key cryptography. And obviously, it will be considered faster because it's using a single key, which is possessed by all the people who are trying to have a communication. And of course, because it's using just a single key, it uses less resources. But if we have to talk about asymmetric key cryptography, it uses one key for encryption and one key for decryption. It's also called conventional or public key cryptography. It is slower because obviously it's using two keys. It uses more resources, because the public key, which is also considered also called the encryption key, is known to all, but the decryption key is different. So the decryption key needs to be different in a way that either both the parties possess it, or one of them or either of them have like a totally different decryption keys, their own separate keys. So we'll see all of that in a minute. So we'll start with symmetric key cryptography first, and then we'll move on to asymmetric key cryptography. So Caesar cipher, this is the most common, the easiest one, and I can bet that all of you are aware of it. So Caesar cipher is the simplest type of substitution cipher in which each letter in the plain text is shifted to a certain number of places down the alphabet. So what happens is that it again depends on you whether you want to take just the alphabet or the alphanumeric character set, which includes alphabets plus the entire number, all the digits. So here I'll be talking about the mathematical description. It includes the encryption function and the decryption function, just like the one we spoke at the start, which was crypto system where we had PCKED. So E and D are over here, and we'll just talk about it. K is the key again. So first I'll talk about the encryption function. So E of X is the function which is equal to X plus K mod of 26. So X is the plain text, a single character from the plain text, and K will be the key. A key will remain constant. For example, it can be anything. If you have to take something very basic, so you can take number 4. So A will be added by 4. So if you add, for example, if I'm taking A as 1, so if I add 4, it becomes E. So that's how encryption is done. But there's also a very important component of mod 26. Why we need mod 26? We need mod 26 only for those cases where the value of K is equal to 26 or more than 26. What if the key is 57? If the key is like 57, we need to divide it by 26, and the remainder will be added to the encryption function, and that's how we encrypt. The decryption function is exactly the same. It just uses the subtraction function instead of the addition one. So here it is. We'll quickly take an example so that it becomes even more clear. For what we have done over here is that we have taken the plain text as sleep, and just give me a minute. Okay, sorry about that. Yeah. So I have taken the plain text as sleep, and the key over here is 57. So I'll just talk about how we can encrypt it. What we do is that we take the value K. The value of K, if we are considering the alphabets, it stands at number 10. So we take the value 10. For L, it's 11. For E, it's 4. For A, it's 0. For P, it's 15. So again, here is the encryption function. E of X is equal to X plus K mod 26. So the first letter for E of K, it will be 10 plus 57, which makes it 67. And then we divide it with 26, and the remainder is 15. So 15 becomes P. Similarly, we do that for L, where we add 11 plus 57 and then mod of 26. It becomes 16, which is Q. Again for E, which is 4 plus 57 mod of 26, which becomes 9. And it is equivalent to J. Again for A, which is 0 plus 57 mod 26, which is equal to 5. And that gives us F. For P, it gives 15 plus 57 mod 26, which is equivalent to 20, which gives U. So here sleep is the plain text, and the cipher text is C equals to PQJFU. We can use the same function, same technique with the decryption function. We just need to subtract the value, subtract the key over here. So I believe it's clear to everyone.
Yes.
Okay, great. So now I think symmetric key, we all have an idea, like it uses a single key, and there can be also different techniques to it, but we will discuss now the asymmetric key cryptography. So firstly, it's very important to understand the Kirchhoff's principle. If you will be studying cryptography, you need to have this in mind. Even if you are not studying cryptography, if you want to set up a secure website, if you want to, create your own messaging application, you need to be aware of this. So what does the Kirchhoff's principle states? The Kirchhoff's principle states that the security of a cryptographic system must depend on the secrecy of its keys only, and everything else, including the algorithm itself, should be considered public knowledge. So it very clearly says that even if the algorithm is known to the attacker, is known to everyone, not just the attacker, we should be able to have a secure communication, and that can be established only if we keep the keys secret. That will happen it can happen in different ways. You have again the symmetric key cryptography, you have the asymmetric key cryptography, but in all the cases, the key needs to remain secure. We have to assume that the algorithm is known to everyone. That's why it's considered like public knowledge. And the focus should always be on not creating an algorithm which is like so advanced that common people cannot do it, but the focus should be on keeping the keys secret, or keeping the keys so complicated that people just cannot try to break it, just cannot brute force it, because the modern day encryption techniques use that concept only. So we'll move to the next part. So this is Diffie-Hellman key exchange. Diffie-Hellman key exchange. So this is Diffie-Hellman, the two computer scientists who came up with it in 1976. So this is a very interesting and a very important encryption technique, asymmetric encryption technique, because this was supposedly the first one where people started to know about public key crypto systems. Because before that, people were just using the private key or symmetric key crypto system, but they were supposedly the first one. There's still, a lot of debates about it, because there's a group of British computer scientists claim later that they came up with the public key crypto system in 1970 itself. So there is a lot of confusion, but still they are supposedly the first one to come up with it. So Diffie-Hellman was the first algorithm which was known so widely, and it was way more secure than the previous ones. So it was very easy to, exchange keys, even in an insecure channel. So it was very important for that purpose. And I really want you all to just pay attention to the next part, because it requires a lot of math, but the concept and the logic is very interesting. So this is how it works. So we have Alice and we have Bob, the two people who want to have a secure communication on an insecure channel. So we can assume that Alice and Bob both have a container which contains a common paint of same color. And then we will expect Alice to have her own secret colors or secret key, and Bob to expect his own secret key. What will happen that we will combine these? They will combine there separately, and then they will exchange those values. So the color that Bob has achieved will be transferred or will be sent to Alice, and the color that has been achieved by Alice will be sent to Bob. So this is what we do. And then they will add their respective colors to it. And at the end, you will see that they have created a common secret key, which no one will be able to decode it. Because, you can assume that this color or that color can be added, but this is just an example. We have taken an example where we are mixing colors, but still in what quantity or like exactly what amount of color should we take, that will never be known by the attacker, because that are known only by Alice and Bob. So Alice has taken a specific amount and Bob has taken a specific amount, but they were given an equal amount of the common paint. They have added their own colors and they have just exchanged those colors. And then they have added their own again. So by this way, they have created their common secret, which which was exchanged on an insecure public, but it was not revealed. The exact color combinations were not revealed. So this is just for understanding. This is just an analogy. This will help you understand that how this works. But because a lot of maths will be involved in it, so this is just for basic understanding. So this is the mathematical description. Sorry. So what Alice does, Alice computes the A is congruent to G of A mod P, and Bob computes B is congruent to G to the power B mod P. So I talk about what these values are. So here you can see the small a and small b are the private or the secret keys of Alice and Bob respectively. Okay, and G is the common value which is known to Bob and Alice as well. The way we talk about the common paint, that same example is applied over here. So what happens is that then they have created A and B, the capital A and B. What they do, they just exchange it. After exchanging it, Alice will compute the same value using her own private key, will perform the same expression, and it will just use the A dash we have taken over here, because we have now exchanged the values. A dash is congruent to B to the power A mod P, and Bob computes B dash, which is congruent to A to the power B mod P. And now we have to just look at how A dash and B dash are equal. If we look at the proof, A dash is congruent to B over A, which is congruent to G over B over A, which is again which becomes G to the power AB, which is again congruent to G to the power A to the power B, which is again congruent to A to the power B. And it hence is equal to B dash. So here we can see that A dash and B dash are same values. So this is how, you know, the two people have exchanged their combination, a specific combination. They have not exchanged their keys, private keys. They have exchanged a specific combination of the keys. And what they have done after exchanging that combination, they have added their own key, own private key. So now it becomes like they both have the same key, which can be used for encryption and which can be used for the decryption purposes. And they both possess like the same key. So that is how the whole mathematical description, this is the whole mathematical description. Actually, I am not providing any example over here where I'll be taking numbers, because the values A and B are prime numbers, and these are like very long 20-digit numbers. So I don't think I'll be able to do justice on like on a PPT, or you will be able to understand that these are very large prime numbers. Even G, which is common, is again a very large prime number. So it becomes difficult for you to, try to brute force it, or, try to do the guesswork of it. So I believe it's clear. Can I get a yes or no answer? You can ask questions if you have.
Yeah, it's clear.
Okay, that's great. So here, just remember that the values that are taken over here are very large values. So that's why we do not, we do not try to do it like we're using small values as well, because this is used a lot even today. You will see that a lot of applications are still using it because it's considered safe. You can exchange your, combination that you have created and then add your private keys. But again, it will remain far from the knowledge of the attacker. So we'll move to the next one. The next part is RSA. Again, it is very common, very popular. It was created by Raivesh, Shamir, and Adelman. It came a year after Diffie-Hellman was created in 1977. So this encryption technique is based on the difficulty of factoring large integers. It again takes very large values, because when we are talking about asymmetric key, it never deals with small values. It never deals with small values. So that's what we have to just consider. And just give me a minute. Okay. So here we'll move to the next part. So how RSA works? Again, it involves, two very large prime numbers, P and Q. And E is the public key, D is the private key. And then we take out the product of P into Q. That's how we do it. And phi of N is another value, where we need to compute this value by, taking the product of P minus 1 and Q minus 1. So this is just a description of how it is. I'll talk about the encryption and decryption technique. Here I have written CT and PT for like encryption text, cipher text and plain text, because we already have P value. So I did not want to mix it with small p and capital P. That's why I've taken the capital CT and the capital PT for cipher text and plain text respectively. So what we do over here, we again take the cipher text, we equate it to the plain text, and we to the power of E. E is the public key, which is known to everyone. And we do the mod of N, which we calculate, which is P into Q. And again, the decryption function is also very much similar, which is PT equals to CT to the power D mod of N. So here is a quick example. Let's say we have P and Q are two prime numbers. So P is 7 and Q is 17. So we take the public key to be 5, where the value of E is 5. If plain text value is 10, then what will be the cipher text value according to RSA algorithm? So I have put up the solution. First, we calculate N, which is P into Q, which is 7 into 17, which gives 119, 119. And then we calculate phi of N. Phi of N again becomes a factor of N. Okay. So here we calculated P minus 1. into q minus 1, which gives 6 into 16, which is 96. So now we talk about the encryption and decryption functions. So here the encryption function is ct equal to pt to the power e mod n. So here the value of plain text is considered to be 10. And we take the value of public key, which is e, to be 5. And then we do mod 119, which is the value of n. And we get the value of plain text is 40. Same goes with the decryption function. We just exchange the places of plain text and ciphertext. And then again, how we can achieve the plain text is by taking the ciphertext, which is 40 in this case, and raise it to the power of 77, and mod 119. We do it, and then we can get the value of 10. So that's how we perform it. Any questions over here? Shall I move to the next part?
Yes, Alia.
Okay. So we are here. We are almost at the end. So I'll just quickly talk about cryptography and steganography. So again, steganography is a very popular term. Cryptography is obviously a very popular term. So what's the difference between these? Just like encoding and cryptography are different, steganography and cryptography are different. So cryptography is considered to be hidden writing, and steganography is considered to be covered writing. So we can say that cryptography basically focuses on changing the form or the format of the text, of the plain text, and presenting it in a way that the attacker cannot understand it, or the attacker cannot read it. That's the whole purpose of it. And the whole purpose and what we are securing over here, we are securing the meaning of the text. But in steganography, we are just covering it. What we are doing is that we are presenting a file, a specific text file, or maybe, in this case, I'll just stick to a text file. So what we are doing is that we are covering, or we are hiding the text file within another kind of image, within another kind of audio file, within another kind of a video file. So that's what we are doing. That's why it's considered covered writing. So that anyone, whenever a layman is presented with a steganographic file, that person won't be able to extract the covered or the hidden file behind it. That's what we are trying to talk about whenever we say steganography. So steganography hides the existence of a message. That's what it is. If you are trying to solve a CTF, you will come across encoding, cryptography, and steganography a lot. So somewhere it's important to be, I won't say to be to be highly qualified in each one of these, but to be able to understand the differences, understand different types of it, so that you can, just look at a specific text and be able to understand that what should I try next. So that should be the whole purpose. I'll move to the next part. So here are, some of the bonus algorithms, which these are advanced algorithms. If you want, you should try. If you're interested in all of this, you should definitely try. This has elliptic curve over the reals. This has LGAML. This has DES. And this has feastal cipher. This has AES and blowfish. So feastal cipher is a very more complicated and a very long structure and cryptographic structure, which is also used by the AES, which is Advanced Encryption System. So feastal cipher, you need to study feastal cipher in detail before understanding AES. But today we use AES the most. So here are two books which I highly recommend. So first one is more of a textbook, which if you want to delve deep into it, you should read. This is the Cryptography and Network Security book by William Stallings. This is like highly recommended. I studied it when I was in college. I studied actually in several semesters, but this also gives you this helps you have that cryptographic knowledge about it, and how network security as well. It has different techniques as well. So this will be a very good textbook for all of you. And then there's Ghost in the Wires by Kevin Mitnick. So it's not a textbook. It's basically a biography of Kevin Mitnick. Kevin Mitnick, the infamous hacker, he is very popular. He is considered to be the world's most famous hacker. So this is a biography by Kevin Mitnick. So there's something very interesting in each chapter. At the start of each chapter, you will have a ciphertext, and every ciphertext is unique every single time. So you are forced to solve those ciphertexts. and the meaning lies in the chapter itself. So once you have read the entire chapter, you can just take that ciphertext, solve it, and you will be able to get specific values. You will be have some questions as well in it, and you can answer those questions. So that is very, very much fun. I highly recommend doing that if you enjoyed the session. And so here we are. Okay, stop sharing. So here we are. I would be more than willing to take questions.